Thank you for the introduction. Yeah, I'm Pia. I'm still a PhD student, and I hope I will defend in a couple of weeks. And today, my talk today is going to cover large parts of what I did during my PhD. And the title of my talk is Generation of Ultrashort Laser Pulses via OPCPA in the infrared spectral region. Don't worry too much if you don't know what OPCPA is, because I'm going to try to walk you through the theory behind that you can all follow. So, these are the two buzzwords of today's talk. So on one hand side, it's the Few cycle. So we're working with few cycle pulses or ultra-short pulses in the infrared spectral region. So if you're, for example, 3 micrometer pulse, then you call it few cycle if you can count the numbers of cycle in the pulse. In this case, for example, it's a 40 femtosecond pulse, just to give you an impression of the pulse durations we are talking about. So why is the infrared region interesting? Here you go. So there are, for example, numerous gases that have characteristics absorption lines in the spectral region above 3 micrometers. And we have also the so-called fingerprint region, where, for example, molecules have very characteristic absorption lines, and that's why it's very interesting to have a laser system running there. So just as a recap, how do we generate ultrashort pulses, or what do we need for that? So first of all, you need a broadband coherent spectrum. So you have like multiple spectral components which have a phase relation to each other, and this pulse then is said to be chirped. So you have like the different spectral components which are distributed over the pulse. So if we add now some phase control and we're able to align all spectral components at a given point in time, then we're able to generate a few cycle pulse, which is then ultimately determined by the spectral width that we have, and this is also called the Fourier limit. So then, if you work with ultrashort pulses at high energies, you run into numerous problems. For example, damage threshold is a problem, and there's a technique which is called chirp pulse amplification, where you start with a few cycle pulse or a femtosecond pulse, and you apply a defined phase to it in a so-called stretcher. So this can be, for example, bulk material or a grating stretcher. And with that, you can make from a femtosecond pulse a picosecond pulse. Then you amplify this pulse, and after amplification, you reverse the phase, so you just apply the negative phase from the beginning in a so-called compressor, and what you end up with is just an amplified femtosecond pulse. So this technique has been awarded the Nobel Prize in 2018 to Donna Strickland and Gérard Mourou. Though the technique has been known from 1985 already, where Donna Strickland developed this technique in her PhD thesis. So this is one part of the title's OPCPA. So this is the chirp pulse amplification part. So what is still missing is the optical parametric amplification. So this is an amplification process that's taking place in a nonlinear crystal and relies on a Chi2 process, where you have an energy conversion between pump pulse and signal pulse, which results in a certain Euler energy. So in reality, we have a pump pulse, which is the most energetic one and also the one with the shortest wavelength, so the one with the most of energy, and a signal pulse, which we send into this nonlinear crystal. There we have to overlap them temporarily and also spatially. Plus, we need a crystal that allows us to make this process efficient. And if we're successful to do that, we basically just take the energy which was initially in the pump pulse and transferred it into a signal pulse and a so-called Euler pulse. In my today's talk, I will spend loads of time just describing how we generate these pump and signal pulses, because this is typically the challenging part if you build an OPCPA system. And if I talk about characterization, I most of the time will talk about the idler pulses. In principle, you can also use signal pulses for your experiment. This is just depending on your application. But in today's talk, I will mainly focus on these idler pulses. So, and to make the title complete, if you add some pre-stretching so that you send in picosecond pulses and you add some post-compression to it to regain your femtosecond pulses, then you have basically what was in the title. So then you have built an optical parametric chirp pulse amplification stage. So the main ingredients for such an OPCPA are that you need a front end, which provides you with all spectral components for all the seed for the pump and the signal. Because this is eventually determining the idler wavelength. So with the pump and the signal, you tune the third idler beam that comes out of the system. You need broad spectra in order to support femtosecond duration, because we're still working in the ultrashort. Then you need a high pump energy, because this is basically then determining your gain to some extent in your system. And if, like here, we're going to work at millijoules at a 1 kilohertz rate, and there the translation is quite easy. So 10 millijoules equals to 10 watts average power at 1 kilohertz repetition rate. So then you need a suitable nonlinear crystal. So the crystal here needs to have a high nonlinearity in order to make this process or to enable a high gain. Then you need low absorption. So ideally for all involved frequencies, so for the pump, the signal, and the idler, which is also sometimes critical, because we work with femtosecond pulses, so we have broad spectra, and like broad spectra from really pump across the signal up to the idler. And last but not least, we need suitable phase matching conditions with broad bandwidth in order to reach femtosecond duration. And at the very end, we also need a suitable stretching and compression scheme, so that we stretch the signal, for example, prior to the process in a way that we can still compress the idler afterwards. And ideally, we can also do some high order phase compensation up to fourth order, for example, to really reach the Fourier limit. So now you might ask the question, why are we making such a complicated system? And this is a bit of the motivation why we are doing this. So we aim for this spectral region here, so above 3 micrometers. And here you see that there are some gas lasers or like quantum cascade lasers which cover the spectral region, but they are either the pulses are too long or the power is not high enough. So in order to reach this area, we use optical parametric amplification. These are the rare earth ions, from which, they're also quite used here. For example, the ytterbium, the holmium, which are typically used for this for front end and to provide the pump and the signal for the OPA process. Some of you might be familiar with the titanium sapphire laser. This is just the working horse of typical OPCPA systems. But what I would like to talk about today is this chrome zinc sulfide laser you see here. In terms of spectral width, for example, it has like quite familiar properties to the titanium sapphire laser. And that's why you also say that the chrome zinc sulfide laser is the teaser of the mid-infrared. So we'll talk a lot about this chromium zinc sulfide laser as our front-end laser today, and I will present 2 systems. So first of all, a mid-wave infrared OPCPA system, which runs between 5 and 8 micrometers, and a second OPCPA, which aims for wavelengths beyond 10 micrometers. Okay, so as I said, there are going to be 3 main parts. One time the mid-wave infrared OPCPA, then the long-wave infrared OPCPA, and eventually I will talk about some application of the long-wave infrared. So I'm going to start with the first chapter. Okay, so this is the chrome zinc sulfide laser, which has a nice spectrum which spans from 1.9 to 2.6 micrometers. And this system provides us with 30 femtosecond pulses. This is just a commercial system we purchased from IPG Photonics, and we have pulses with 12.5 nanojoules of energy centered roughly at 2.4 micrometer. And now we use this chrome zinc sulfide oscillator to seed our pump and the signal for our OPCPA. So we do that by just using the dichroic mirror. So we split the spectrum roughly at 2.1 micrometer, and we use the lower part of the spectrum to seed the pump and the upper part to seed the signal. So the signal we checked has still a pulse duration of 41 femtosecond, which is short enough for our application. So let's come to the pump. Our pump is a regenerative amplifier, which is a resonator in double X-fold architecture, or just like double X-fold cavity, so a resonator. So in principle, pulses can just circulate around. We have a holmium-ILF crystal as a gain medium, which is self pumped by a thulium fiber laser. So, and then we couple in the 2 nanojoule seed from our chrome zinc sulfide laser with a pocket cell and a lambda half plate, with which we can trigger the number of round trips. So, and then the pulse circulates around, and with every pass through the gain medium, it accumulates more and more energy. And after 19 round trips, we're coupling this pulse out again, and now we have 13 millijoules of output power. And in numbers, this is a gain factor of 10 to the 6, which is high enough for our application. So to put this into numbers, I come back to the picture I've already shown you. So this is the spectrum we have for our pump source, where we use a trap volume Bragg rating to elongate the pulse, to stretch it to nanoseconds, and select the wavelength region of interest. Then this is amplified in a preamplifier. This is a thulium fiber amplifier, and these pulses are then coupled to the regenerative amplifier I was just talking before. So, and after circulating around this regenerative amplifier, we end up having pulses which are centered at 251 nanometers with a bandwidth of 2.7 nanometers. The energy that we get out of that is 13.4 millijoules, which is the highest regenerative amplifier at 2 micrometers so far. We have a nice intensity profile and a reasonable low root mean square deviation. So, and then we need to remove the residual chirp from this pulse, so we send it into a grating compressor, and with this grating compressor we were able to show that we have a pulse duration of 2.4 picosecond. So as I didn't know how familiar you are with pulse duration measurements in the pico and femtosecond range, I just quickly want to recap on how we measure this pulse duration. So photodiodes are just too slow. So what we do, we build something that's looking almost like a Michelson interferometer, where we have an input pulse which is split in a beam splitter into 2 replica, and we have one arm that is set onto a translation stage, and then we have a lens that is focusing the 2 replica into a nonlinear crystal or a Chi2 medium, and then we get a signal which is frequency shifted, as you see here, which is depending on the overlap between the 2 pulses. So with that, you can decouple the time domain into like a spatial domain, and this is something you can then record. And if the detector is a photodiode, then you say that's an autocorrelation. And if your detector is a spectrometer, then you say, then you get a frequency resolved optical gating trace, or short a frog trace. And I will have, in my talk, I will a couple of times talk about or like autocorrelation traces and frog traces. So to come back, so here is the pulse duration of the pump. So you see here the D-day, you introduce on this arm, and the second harmonic signal you get into this from this Chi2 crystal. Okay, so now I have talked about the pump. Now we come back to the signal. So the signal is the remaining part here, so it's centered at 2.4 micrometers with 10 nanojoules of energy, and here again we have an autocorrelation trace which shows us the 41 femtosecond, and then we send this pulse into a high nonlinear fluoride fiber. So this is a so-called Ziebelin fiber we use with a quite large nonlinear refractive index, and we do something that is called Soliton-Raman self-frequency shifted pulses. So don't worry if you don't know what a soliton is. I will talk about it on the next slide. The interesting feature about this fiber is that it has negative dispersion beyond 2 micrometers. So we have simulated that from the properties we got from the fiber and the geometry. And yeah, the thing you need to remember is that it has negative dispersion above 2 micrometers. So if you send an ultrashort pulse into a fiber in general, and this fiber has a dispersion, you end up having a lot longer pulse duration because the different spectral components inside the fiber, they travel with different speed, so the pulse gets dispersed. But there is another feature. If you have a short pulse and a nonlinear fiber with negative dispersion, you have the effect that you can create solitons, and in this case, you have the same temporal shape because negative dispersion is compensated by self-phase modulation. So you don't have the broadening. So we use, this fiber I was just talking about is such a nonlinear fiber with negative dispersion, and on top of that, we add some Raman frequency shift along the fiber, and this is simulated in the following. So with some program, we just simulated how the spectrum evolutes inside the fiber. So you have here the fiber distance, it's 2 meters in such a Ziebelin fiber. And you see that from this, the input spectrum, you have a soliton that just grows out of it and then shifts towards longer wavelengths over the propagation distance. So we checked if this pulse we get here is really a soliton, and I can confirm from this autocorrelation measurement that we have a nicely femtosecond pulse at, for example, a wavelength of 3 micrometers. So this is our signal we can now use for our OPCPA. And another nice feature about that is that the different spectral components, according to the simulations, just travel at different speeds into the fiber. And if you think back at the 3 picosecond pump source, you can now nicely select just one pulse and not running into problems because you, for example, amplify spectral components you don't want to have. So, from this, I can just say that we now use this signal soliton for our OPCPA with a few nanojoules of energy. So this is much more than other systems have. Like other systems sometimes start with picojoule pulse energies. And the nice feature also is that this soliton is now tunable. So we can tune it between 2.8 and 3.2 micrometer just by changing the intensity inside the fiber. So how does it look like? So on the top you see the spectrum from our chrome zinc sulfide oscillator, and with every line you have different energies that were coupled into the fiber, and you now nicely see that we create a soliton that really shifts towards longer wavelength depending on the input energy. And with that we have a very simple system where we can basically tweak our signal frequency for our OPCPA. Okay, so let's come to the setup. So we have here our front end with the chrome zinc sulfide oscillator at 2.4 micrometer. We have our dichroic mirror, which splits into 2 parts. The 2 micrometer part, which is used for the regenerative amplifier, and the remaining part, which is sent into the Ziebelin fiber, which creates our tunable signal with roughly 75 femtosecond. And then the whole setup looks like the following. So we have our signal path here, which we stretch in some bike materials. We have an AOPDF, that's our short Dazzler, that's an acousto-optical programmer's dispersive filter. You can add some polynomial phase onto the signal with that. So this is our higher order phase compensation in our system. And then we have two amplification stages. So the first with very low energy from the region, and both stages are based on the nonlinear crystal zinc germanium phosphide. And then after the second amplification stage, we have now tunable signal pulses with up to 600 microjoules of energy, and we have a tunable idler wavelength between 5.4 and 6.8 micrometers with up to 400 microjoules and less than 100 femtosecond pulse duration, but this is details I will come to now. So we measured the spectrum of the signal and the idler we get out of the system. So on the left-hand side you see the signal spectrum, and on the right-hand side you see the idler spectrum. And from the color code you nicely see that if you tune the signal, you also tune the idler. So just by changing the pulse energy, we can shift the signal wavelength in our system. We get a tunable idler between 5.4 micrometers and 6.8 micrometers, and the spectral width of up to 4.3 terahertz allows for a Fourier limited pulse duration of 73 femtoseconds. So now you might wonder why we have these lines on top of our idler spectrum, and the answer is fairly easy. This is just absorption lines in air, so this is just water absorption, which is a huge problem in this spectral region. So in order to do further experiments and to characterize, we really need to purge the whole system, which we did with nitrogen. So the next measurement you see, we implemented all this. So we purged the system, and now you see the so-called frog trace. So on the upper left, you see the frog trace that has like the delay, for every delay point, a whole spectrum. Just to give you a feeling, like this is a measurement that takes roughly 45 minutes, because in this wavelength region you can, you only have like monochromators, and that's why you need for every single delay step roughly 40 to 50 femtoseconds of measurement time just to record one spectrum. So you need quite of a stable system to do that. And we could reconstruct this frog trace with an error of less than 0.7%, and you nicely see that the retrieved spectrum coincides with the measured spectrum, and we could also show that the pulse duration is 99 femtoseconds. Okay, so to sum it up, so this was the mid-wave infrared OPCPA with our tunable idler pulses, compressed down to 99 femtoseconds, and this is a system that runs up to 400 microjoules of energy at 1 kilohertz repetition rate. So now I want to go to the next step and go even further. So we're now aiming for longer idler wavelengths. Now we are looking, now we have explored kind of the lower region, and we're now aiming for wavelength above 10 micrometers, which is a very unexplored area so far. So we come back to our front-end setup you've seen at the beginning. So the chrome zinc sulfide laser with a dichroic mirror seeding the pump and the signal. But this time we directly use the signal at 2.4 micrometers to combine it in our OPCPA, and with that we immediately create our long-wave infrared OPCPA at 12 micrometers. So, and this is a great system because this is really compact and there are no nonlinearities involved. So in reality it looks like the following. So we also pre-stretch the signal pulses, which we then pump in 3 optical parametric stages in gallium selenide. So we have a first non-collinear stage that amplifies the pulses to 15 microjoules. So from the nanojoules we got to microjoules here. Then we stretch further with bulk material. Then we have a second Second parametric stage, where we already achieved 140 microjoules of signal, and then this is changing a bit from before. We see the last stage with the idler, and in this last stage we're able to amplify the idler up to 70 microjoules, which is really record-breaking in everything, like in wavelength systems above 10 micrometers, and this is then centered around 11.4 micrometers, which we compress with bulk material. So this is just zinc selenide we put here. And in the next slides, I want to talk about the characterization of this long-wave infrared idler. Okay, so let's start with the signal. So on the bottom here, you see the seed spectrum we have in theory, or not like we have in the experiment from the chrome zinc sulfide laser. And when we amplify this spectrum, we had to realize that we are losing half of the spectrum just because of phase matching properties. So these bars here indicate the phase matching in gallium selenide for our 2 micrometer pump. And unfortunately, gallium selenide just prohibits us to amplify much below 2.4 micrometers. So unfortunately, we lose a bit of spectrum here. But still, we have a spectrum with 79 nanometers, which is still broad enough for our application. So, and this signal then translates into an idler, which where you can see the spectrum here. So you see it's centered at 11.4 micrometers with 840 nanometers of bandwidth, which in principle supports a Fourier limit of 172 femtoseconds. We get an average energy of 65 microjoules out of it, with a reasonably okay stability, but a nice beam profile. And all this corresponds ultimately to a conversion efficiency of 2.5%, and a quantum efficiency of 15%, and we are pumping the gallium selenide with 50 gigawatts per square centimeter. So at this point, we just wanted to find out how long the pulse duration is and make some adjustments to it, and we found that here we have 183 femtoseconds. And you might just realize these little bumps on the left and the right-hand side. These are unfortunately coming from our uncoated gallium selenide we have in our autocorrelation setup. So this is a feature that does not belong to the pulse. This is just the fact that you cannot anti-reflection coat gallium selenide, just as a hint here. And we wanted to just see some more phase information, so we did also frog measurement here. Again, same problem. We have for every delay point like 40 femtoseconds of measurement, so it's like 1.5 hours to record this frog trace, which makes like all the higher order phase compensation quite tricky. So, and here you could see that we could reconstruct this this trace with an error of 0.4%, and again we have the reconstructed spectrum is nicely coinciding with the measured ones, and happily we are reconstructing the same pulse duration as we had with the autocorrelation trace before. So then we ask, okay, what can we do with that? That's the big question of developing laser sources in general. And so we came up with an experiment to make some nonlinear spectroscopy in water. So this is a fairly simple setup. So we have like this output idler from our OPCPA. We compress the pulse duration. Then we have a polarizer to change the energy. And then we just simply use lenses to focus this down into a water cell. This water cell is made out of 2 barium fluoride windows. I can just say at this point we initially tried with diamond windows, but they break quite fast. Like we kind of put black dots in it, so there must be some carbonization going on. So barium fluoride was the only window that actually worked for us. Then we have a spacer here, which allows us to introduce 12 micrometer of water, and this is not flowing, so this is just put inside and just use how it is. And then we just send the idler through it and just record on the other side with some additional lenses the transmitted light. So, and what, if you ask what do we want to see with that, so there's a librational L2 mode, so a hindered rotation of water, which is roughly at 660 inverse centimeters, so 14 micrometers roughly in wavelengths. And you see the green is the input spectrum from the OPCPA. I just want to emphasize that this is normalized, so the purple one is of course very much smaller. And then the transmitted, you see that the spectrum which is towards the peak of the absorbance is more likely to be absorbed. So we can now directly excite this, for the first time, this librational mode, which no one has done before because there was actually no energy at that wavelength. So, and that's what we measured. So on the x-axis, you see the energy of our long-wave infrared pulse, and on the left-hand side, the transmission. And we could show that between 3 and 27 microjoules of energy, we could see a change of 1.4% in transmission. And now we try to interpret this and to make some sense out of it, and that's why there was a simulation I did. So actually we had a look at the librational mode in a kind of quantum picture, so with a lower and an excited state. And with the laser pulse, we excite the water molecules from the ground state to the excited state. And by doing this, this water molecule becomes kind of transparent for the photons that come after. So in before this water molecule reaches its lifetime and decays from the upper level to the lower level, it's kind of invisible for the other photons in the same pulse. So, and then we tried to write this in terms of the rate equation, which looked quite similar to the laser rate equations we all know. So we have a population density N1 and N2. We have an absorption coefficient, which is then changing with the intensity of the laser, and some decay time or lifetime with which the system decays from the upper to the lower state. And then we included some numbers, like how many molecules we expect, how large the radiated area is, and then you can find some absorption coefficient, which is then proportional to the population inversion and the absorbance of the water molecules. And from this, we try to kind of estimate and calculate the transmission in the water sample. And that's what we did. So I put now two more lines here. So this is the expected transmission just from this very simple quantum picture for a 10 femtosecond and a 20 femtosecond lifetime, which changed where you can see that the data is somewhere between. There has been other work where people were indirectly exciting water at these frequencies, and they also found both papers basically agree on that the lifetime is lower than 100 femtoseconds, but we are not experts in water spectroscopy, so I'm really curious what you say about it. Okay, and with that I'm coming to the end. So I was talking today about the OPCPA in gallium selenide in the long-wave infrared spectral region above 10 micrometers with a front end which is at the same time seeding the pump and the signal without nonlinear stages. It is a very powerful system. It has a record energy of 65 microjoules at 11.4 micrometers with 185 femtoseconds, which corresponds to less than 5 optical cycles. And for the first time we could directly excite this librational L2 band, and we were trying to estimate the lifetime from this, which we kind of put below 20 femtosecond, which is just an estimation. Okay, and with that, I thank you for your attention. I thank all my colleagues for technical and mental support. Yeah, and I just put the other, like all the relevant papers, you can also find the data I was talking about today in. Yeah, thank you.